Hello, everyone. So today we are going to discuss Pascal Triangle, which is a very important mathematical artifact produced by the French mathematician and physicist and philosopher Blaise Pascal. And basically, in fact, let me show you. I already printed one, so let me switch here. Okay, so here is Pascal Triangle. And as you can see, this triangle starts with one. In fact, it has one at the beginning and ending of every line, and every line or every row you go down increases by one element. So you start with one element, then two elements, they start with one, end with one, and then three elements start with one and end with one, and so on and so forth. The middle number here is the sum of the two above it. So this 15 is 5 plus 10. This 28 is 21 plus 7, and so on and so forth. We call the first row the zeros row, okay? The zeros. So if I refer to n as the name or the number of the row, that would be 0, that would be 1, 2, and so on and so forth until here I have 10. Think of it as the first entry after the first one. The first one or the leading one, the first entry, there is no entry, so it's 0. Here, the first entry is 1. Here, the first entry is 5. Here, the first entry is 10, and so on and so forth. Why do we call these, or how did we construct that? If you want to think about how to use points to draw a triangle, so for example, if I tell you, I want a triangle with a height of 0, you say, how? The triangle will collapse until it becomes a point, right? So it's only one point. If I want a height of 1, then I would place a point here and a point there. And now I have a triangle of height 1 if I consider the height between every row and the succeeding row is 1. If I want to make it of size 2 or height 2, I will add 1 here, 1 there, and 1 in the middle. So there would be 6 points. If I want them 4, I would add 1 here, 1 there, and 2, and altogether they become 10. I want you to look at this diagonal. 1, 3, 1 plus 2, 6, 3 plus 3, 10, 6 plus 4. And we call these numbers triangular numbers for that reason. So you see, if the height of the triangle is 1, we call n is 1. If the height is 2, then it's 2. If the height is 10, it's 10. These are some quick observations, okay? Also, the sum of every row is 2 to the power of n. 2 to the 0 is 1. 2 to the first power is 2. 2 square is 4. 2 cube is 8, and so on and so forth. So that becomes very helpful with the binomial distribution in statistics or in probability, so to speak. A very special case. Suppose I'm tossing a fair coin. So there is a 50-50 chance of getting a head or a tail. And I'm going to toss it an even number of times. Okay? And I want you to find what is the probability that I end up with half heads and half tails. For example, let's say I'm going to toss it 10 times. And I want to find the probability of getting 5 heads and 5 tails. The answer is very simple. First of all, there are 2 to the 10 ways of getting heads and tails if you toss it 10 times. I'm not going to ask you to count them, but you can check with like 2 or 3 tosses and you see that the answer is 2 to the n. So 2 to the 10 is 1024. If you have like a computer, you have seen this number a lot in memory, right? You know that. But what goes into the numerator? funny thing is just when the probability is 50-50, okay? So it's a binomial distribution, meaning you have only two possible outcomes. We call them usually success and failure, or you can call them head and tail, yes or no, pass, no pass, anything, any experiment that has only two possible outcomes. And if they are equally likely, be careful here. This is the trick. They have to be equally likely. If not, then of course, all what I'm saying here won't work. You have to do the math to find the probabilities. What is the probability of getting five heads and five tails? I want you to see that any row here is symmetric. You can read it from right to left or left to right. Okay, so it really doesn't matter. If we consider the number of heads as the success, you can consider the number of tails. But if you consider the number of heads, the first entry is the probability of getting no heads in 10 trials. So you get 10 tails. This probability is 1 over 1024. What is the probability of getting only one head or one tail for that matter, and 9 of the other? It's 10 over that. The probability of getting 2, 3, 4, 5. So the probability of getting 5 heads and 5 tails is 252 over 1024. That's one very quick application of Pascal Triangle, and it's one of the many that I'm sure there are too many hidden there. I don't even know about them. Okay, so that's one application. Another application is the binomial expansion. So if I tell you, can you expand x plus 4 or minus 4, for example, minus y to the fifth power? Where do I get the coefficients? I know that the first element, I mean, if I start with x, would be x to the fifth. Notice the sum of the powers has always to be 5. So x to the fifth, and then x decreases by 1, and the y that didn't appear here, meaning it has a power of 0, becomes the power of 1. And then I will have an item that has x cubed y squared. Notice 3 plus 2 is 5. And then x squared y cubed. And then x y to the fourth, and then y to the fifth. So they have to be 6 elements. Think of x plus or minus y squared. You get 3 elements, right? Now, what are the coefficients? Well, very simple. This is 3. This is the row of 3s, 4s, and 5s. Notice, it's when the first element after the 1 is 5, this is where you go. You read the first coefficient is 1. So 1, I'm not going to write it. We usually don't write 1. Okay? The second is 5. The third is 10. The fourth is 10. The fifth is 5. And the last is 1. If that was x plus y to the fifth power, then all the signs would be positive. If it's minus, then they alternate. You always start with positive, and then negative, and then positive, and then negative, and then positive, and then negative. And you're done. See how easy now you can construct any binomial. You can expand any binomial uh, power like that, or any power uh, expansion. One more thing, in fact, there are too many, but I'm going to show you a few here. If I go along, we said if you go along this diagonal, you get the triangular numbers. We call them the triangular numbers. But something else. If I pick, notice that if I start before the triangle, there are like some zeros here, right? There is nothing, so we call it 0. If I take 0 plus 1, I get 1 square. If I get 1 plus 3, I get 2 square. 3 plus 6 is 9, which is 3 square. 6 plus 10 is 16, or 4 square, 5 square, 6 square, 7 square, and so on and so forth. Nice. right? Also, um, have you seen the Da Vinci Code movie? If you have, you might have heard of the Fibonacci series. And the Fibonacci series, again, there are, in the literature, there are many ways to describe it, but basically, if you look, if you make a diagonal like that from Pascal triangle, where is, yeah, 2 and 1, and then 1, 3, 1, maybe I didn't incline it correctly. 3, 4, 1, 1, 6, 5, 1, and you add the numbers. You get 1, 1. Oh, I keep picking this. I have to throw it away. I'm sorry. 1 plus 1 is 2. 2 plus 1 is 3. 1 plus 3 plus 1 is 5. 3 plus 4 plus 1 is 8. 6, 7, 12, 13, 21, 34. These are the entries of the Fibonacci series. So the Fibonacci series somehow is embedded in Pascal triangle, like the triangular numbers, like the squares, like the binomials, like the binomial distribution, all of these. And you should have known that if I divide each two, first of all, uh, the Fibonacci series that is where if every element is the sum of the preceding two. We start with one, you know, and then the next one is 1 plus whatever is below, and there is nothing, which is 0. So 1 plus 0 is 1. 2 is 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3, and so on and so forth. If you take the ratio of every two consecutive numbers, so I divide 1 by 1, I get the minimum, a minimum number, which is 1. Then I get 2 over 1, I get 2. Then 3 over 2 is 1.5. And then 5 over 3 is 1.667. Then 8 over 5 is 1.6. Then 13 over 5 is 1.625. And you keep going slightly to the right, slower, shorter period to the left, shorter even to the right, until these numbers will converge to phi, which is the golden ratio. Isn't that funny? So all of these are embedded here and even more. Now, let me get another piece of paper, and I'm going to assume if x is any fraction between 0 and 1. And I ask you, so here, expand the following. And the absolute value of x is less than 1. What is 1 over, let's say, 1 minus x? You say, how can I expand that? It's 1 over 1 minus x. Say yes. But if x is very small, you know what you will get? Meaning x is less than 1. You will get 1 plus x squared plus x cubed plus till infinity. Let me show you something very interesting. Suppose x is 0.1. 1 over 1 minus 0.1 is 1 over 0.9. Take your calculator and calculate 1 over 0.1. What do you get? No, I'm sorry. I said 0.1, so 1 over 0.9. No, right? 1 minus 0.1. I'm sorry. You see what you get? You get 1 plus 0.1, which is x, plus 0.01, which is x squared, plus 0.001, which is x cubed, and so on and so forth. Not only that, in red, I'm going to expand 1 over 1 plus x. If you divide by plus x, you get 1 minus x plus x squared minus x cubed plus till infinity. And you say, okay, nice, but why do I care? You know, you don't have to care. What if it's 1 over 1 minus x quantity square? What you get there? Okay. I say, I don't know. That's a lot of work. I say, yes. And here is Pascal Triangle to the rescue. When I divided 1 over 1 minus or plus x, I use this diagonal. What do you mean? It means I say 1 plus x squared plus x cubed plus x to the fourth. So 1 plus x raised to the power of n plus x raised to the power of 2 plus x raised to the power of 3 and so on. So what do you expect if I divide 1 minus x squared? Yes, I will go to the next diagonal, which has 1, 2, 3, 4. So it's 1 plus 2x plus 3x squared plus 4x cubed plus till infinity. And of course, if it's plus, then you alternate the signs. Nice? Okay, so one for you to try. What is 1 over 1 minus x to the fifth power? Where do I go? If this is x squared, x cubed, x4, x to the fifth. Again, I go to the diagonal that has a 5 after the first one. So it's x plus 5. I'm sorry, it's 1 plus 5x plus 15x squared plus 35x cubed plus 70x to the 4 plus to infinity. And if it's positive, then you alternate the signs. Okay, so that's another indirect application of the Pascal triangle. I don't know if that's long enough. Maybe I'll pick it up in the next video to show you something very interesting. You will find it in advanced math textbooks, but I'm gonna keep it as a surprise for you when we meet next video. It's really mind-boggling. Thank you very much for your time, and I hope to see you soon. Okay, let me stop the video. Okay, thanks.